The last speaker of this session is Oksana Zaharko from Paul Scherrer Institute. And the talk is entitled Altermagnet Manganese Fluoride used by inelastic neutron scattering. So please, Oksana, the floor is yours.
Thank you so much. Do you hear me? Yes.
Yes.
Do you see me? Yes. And I hope you see my slides, right? So it seems I'm ready. Oops. I wanted to take a laser point. Right. So first of all, I really appreciate that I can participate in this workshop. It's really great from the point of view of people who attend. And honestly, I should say that I'm also Ukrainian. I left Ukraine, I think, in 1993, looking for a place where to do science. And so I landed in Switzerland. In Switzerland, doing neutron scattering, this is Paul Scherrer Institute, where we have actually this large-scale facilities. We have neutrons, muons, we have synchrotron, we have X-FED, so actually all what scientists can dream about. My topic is today Altermagnet manganese fluoride studied by inelastic neutron scattering. And the outline, for sure, this will be the main part, so part 3, but I want like to come a bit to definitions, to recall, to briefly explain to those which are not very familiar what neutron scattering can and what it cannot, and also probably put our results in perspective of other findings about the material. So definitions, I think we had beautiful, great lectures of Yarrow, of Libor, and I really enjoy their definition of altermagnetism, which for me as experimentalist sounds this way, correct me if I'm wrong. This is actually a theoretical concept and it is related to a symmetry. And it is a symmetry concept when we don't have spin-orbit coupling. So therefore, we can use spin groups to describe the symmetry properties of the material. In the real space, in the direct space, in the crystals, we then are confronted to the opposite spin sublattices. We are talking about classical spins, up and down arrows, but they are connected by rotation, not by translation or inversion. This gives in reciprocal space, in momentum space, great advantages because then you have a spin split states in electronic structure. And this is probably the part which is the most interesting for applications, for devices. And as there is like a huge amount of k equals 0 opposite spin sublattice collinear structures, this is actually like a golden place to seek for good devices. Though I should probably mention that there is a lot of theory, a lot of predictions about altermagnets, but there are very little of real system which actually are really so well explored that we can say, yes, we use that. I like also another definition of altermagnetism. This is given by Paul McClarty, which also had a presentation here. Unfortunately, I had experiment. I was not able to join. But in his article, on their article in PhysRef B, he's mentioning besides collinear sublattices, besides compensated magnets, he's mentioning magnons, and he's mentioning multipolar order. And here I decided, okay, I put these googles because Jara today in the morning did, I think, very nice allegory not allergy, to what one sees with different methods. And when we look on the magnetic order with dipole approximation, we see these nice arrows going up and down, and we are talking about opposite compensated magnets. But if we would put another googles, then probably we would see a bit richer physics, not only a dipole apart, but more. Right. In the same article, they used actually manganese fluoride to show what happens in the magnons because of altermagnetism. And this is like a classical material. You have, besides magnetic order, you have the moments which are oscillating in the long range fashion, and you would have spin waves, which in specific directions, and these are directions in diagonals, 1, 1, 0 and 1, minus 1, 0, you would have split of otherwise in other places degenerate modes. And the splitting would be exactly because of altermagnetism, because you will have actually even two chiralities. And this plot from this article actually shows how at different energies you would have different splitting, and the largest will be close to the I think one half. So one quarter, 1 in L, for example. And this huge, I would say, splitting, at least it's very nicely visible in paper, you would see if the ratio between J11 and the J between sublattices, which we name J2, would be like minus 0.25. And for another diagonal, for 1, minus 1, 0, this would be minus half. So it was like for me, as for neutron scatter, immediately clear that I would like to see that splitting, especially it's promised to be quite significant. But probably back to the manganese fluoride and to history, actually, this was one of the few materials which was used to really prove the concept of antiferromagnetism by neutrons. So first it was neutron diffraction, and here you see two patterns, right? This is in paramagnetic state. You have 3, might be 4 break peaks, and when you cool it down, you have one more break peak, and this is 1, 0, 0, and this is actually the antiferromagnetic peak, magnetic order. Now from the right side, you should see the structure. And for sure, we don't measure structure with neutrons. We make a Fourier transform to get, so there are many models which can fit the same diffraction pattern. So actually you have to come with several ideas and check them against the observation. What you should remember also that neutrons do not see the whole magnetic structure factor, but they see only the projection orthogonal to the Q. And what you also probably knowing from course of X-ray scattering, diffraction, and spectroscopy, that for neutrons, the nucleus would be a point scatter. So the structural, the nuclear structure factor would be, form factor would be a constant, while for magnetism, it will be depending on the angle of the scattering on sine theta over lambda. This part which I plot here is the just dipolar part. But if one talks about more complicated things, there will be also contributions at larger Q, much smaller, and under more complex approximations, I mean, if there will be quadrupolar, octupolar, or other scattering. So even in diffraction, especially if you do polarized neutron diffraction, you would see this more complicated structures than just up, down, up, down. And by the way, in the very beginning of the neutron scattering, there was actually quite a number of experiments trying with polarized neutrons to see beyond the dipole approximation. And manganese fluoride was also a subject of such study. And they have seen that the spin density is located not only on manganese, it's a bit transferred to fluorine. But these are very complicated experiments with very limited data you get. So actually to see much more, it was not possible. Right. Besides elastic scattering or diffraction, people name it, sometimes you can also use neutrons in elastic channel, meaning that you are changing not only momentum where it flies while interacting with matter, but you also measure the change in energy. And though the 99% of neutrons will be elastically scattered, there will be some which are inelastically scattered. And this is the setup of such experiment. You have sample, you pick up the neutrons which are having special Ki, so the incoming momentum. You pick up by another crystal also neutrons which have the momentum which you want, and you also detect the energy of that neutron. This setup and also much more about neutron scattering is nicely explained by a manual or a textbook or chapter which is named Neutron Scattering Study of a Classical Antiferromagnet, Manganese Fluoride. And I actually thought it's really cool thing to show it here because also like 10 years ago when this manual or this textbook was written, people were considering manganese fluoride only as antiferromagnet. This is the machine which we were using for our experiment. This is a bit more complicated. This is named CAMEA at ThinQ, at our spallation source. So it is more complicated because we have a bit more of analyzers than one and a bit more of detector than one. So we try to get more out of the experiment just because the neutrons are limited and we want to measure in the reasonable time. So in the same manual, actually, or this textbook, it is also explained what you get from the measurement, right? You are measuring some peaks, energy transfer and intensity at specific Q values, and you then build dispersion, right, which is somehow related to your spin waves. And once more, you're not measuring Hamiltonian, right? You have a model, you have some effective Hamiltonian with some J's, which are first coupling, second coupling, whatever. And then you fit this observation to this model, and you are getting how good the model fits. And usually the simplest way is to use linear spin wave theory. Once more, you are having dipoles, classical arrows which are moving in a coherent fashion, and you can get then this J1, J2, or whatever couplings, and anisotropy and other terms. So in that manual and in 2 or 3 other articles which were done in the beginning, at 10 or 20 years ago, people always consider J1, J2 couplings and the single ion anisotropy for the system, and everybody was happy with the fit of inelastic neutron scattering data. Now, to think about altermagnetism in manganese fluoride, you should go a bit beyond. You should consider other couplings, further couplings, so these diagonals. If you would count them according to the distances, this will be actually a 7th coupling, which is not very close. And you would need to look into specific directions of the reciprocal space, so which will be related to these 2 directions in the direct space to see these couplings, because in majority of, or to be sensitive to them, because in majority of other spaces, actually, you would be not having splitting between the spin waves, right? So you should go somewhere between gamma and M point, you should go somewhere close to A point, and only then you have chance. So as for neutron scatter, this material was antiferromagnet, we decided, okay, we try to do that experiment and go into these directions. So this is actually the 3rd part of my story. That's the experiment by itself. We had a huge crystal, 3.5 grams. This crystal was once more test crystal to check that spectrometer works well up to the moment of altermagnetism. And we collected data in 3 different scattering planes, in HHL, in HK0, and H0L. So all paths in the Brillouin zone which are can be interesting. And the most interesting, as I already told, should be this with A and M points. And if you see, like in this overview of the data, not much splitting is seen. This is once more cuts in the Q space at different energies. So what we did, we tried to improve the resolution, made different instrumental tricks to go as good as we can. That's really state-of-art splitting, the instrumental resolution you can get. And maximum which we were able to get, that's actually 3 couplings instead of 2, the 3rd one, which is very, very small. and probably also with a sign which is different from what was expected, because this is ferro, antiferro, and this is ferro. It was previously reported it should be antiferro as well. We also tried the dipole-dipole instead of single anisotropy, because actually manganese iron might be quite spherical electron density distribution. So let's try two giant manganese atoms interacting to each other by dipole-dipole interaction. We cannot actually distinguish that from our data from single anisotropy, so we stayed with the simplest model. And that's the cut which I was talking about, which might be important. So this is A point, and this is M point. And you see that's how altermagnetic splitting should look like, the white line. And this is the splitting when the difference between J7A and J7B, and so these two diagonals would be 20 microelectron volt. What is important is not the value of this J, but really a difference between them. So our data show that there is no altermagnetic splitting within the resolution of our experiment. That's what I should say. So we managed to publish that information, and Vincent Morano, who is the main author, or the main actually so the one who was a principal, I would say, investigator, he named it really straightforward. It's absent of altermagnetic magnet band splitting in manganese fluoride. But for sure, one should say it was not detected with our resolution. If the resolution will be 100 times better, for sure we might be seeing that. Now, I don't stay negative. And actually, one of our referees was telling, okay, if there is no splitting, it is not altermagnet. What is the point to publish that? I think it's very important knowledge, because it is altermagnet. It is just showing not the properties which one would be thinking. I mean, the splitting is there, but it's probably very small. Maybe one should use other tools to see the altermagnetic properties of this manganese fluoride, and a lot of publications actually show that it is altermagnet. We can only from this experiment, we can only say that this J diagonal, they are not that different as one expected. And here I refer to the article of theoreticians who actually also did took manganese fluoride as an example of how to calculate multipolar expansion of the spin density. And they show that actually you should have octupoles with specific symmetries of this O3 to minus octupoles, which are ferroically ordered in manganese fluoride. And here down, I actually have from their paper, the plot of how this octupolars are looking for manganese site 1 and site 2. So it's not far from, let's put, it is because of we have different surrounding by fluorine of our manganese A and manganese B sublattice, but it is also what they estimate is very, very small. So I want to stay positive. I think it is altermagnet. We just study these very complicated materials with different glasses. We see different things because sometimes it is a huge effect and you see it immediately with, let's put, conventional methods. Sometimes you really need to go deep, and maybe even some method is not like correct for this particular property studying. I know that manganese fluoride has interesting properties like piezomagnetism, and that's probably the level one should prove or disprove and see how altermagnetic splitting really affects the properties. And would you say that the neutrons are not useful at all? I wouldn't say that's so. I would say that there are systems where one sees magnon splitting, for example, manganese telluride. I'm sure there will be more of these examples coming. There's just the question to find the correct a correct system, and it's a question to find or to grab what is the correct origin of this or this phenomena, because I believe that manganese telluride is having probably more anisotropic exchange coupling because it is some report metal, some report semiconductor. So the exchanges are further extending. And even if it is J10, J11 from the distances, they can be quite important. Thank you, I finished.
Yeah, thank you very much. So now we have a time for questions, so please. Oh, please, yeah.
May I ask some simple question? Some simple question.
So the first is Jeroen, please.
I'll go first. Oh, thank you very much for your talk. You already the question. Well, a question would be, why is it so small? And you already gave a indication saying that the gap in manganese difluoride probably is quite large. It's an insulator, so there are short-range interactions.
Yeah.
My question would be: is there a theoretical estimate that of this say altermagnetic J in this system? Is it indeed smaller than 120 micron electron volt?
You know, that's exactly, I think, a very good question. We came to this experiment exactly to answer it from experimental point of view, because up to now, even DFT calculations were done up to level J1, J2. The theoreticians which were showing that this is altermagnet just were showing some arbitrary or absolute units which you cannot relate to experiment. So when whom I was asking before doing experiment, how big will be the splitting, nobody was able to answer.
Okay, thank you.
Thank you. So now the question by Yuri, please.
A very simple question. I deal with this manganese fluoride a long time ago, and I remember there is some Dzerzhinsky-Moria interaction, which can be manifested itself, namely in the spin wave close to the gamma point, but maybe also it can manifest itself at the break points also. There is some. Do you include this possibility?
Honestly, we didn't calculate. Because once more, I think I tried to make this very generic introduction, which might sound a bit too like for students, but you know, we have a model, and we have a model which fits the data so good that actually we don't need extra parameters. Dzerzhinsky-Moria would give some anisotropies, but our data do not show that. Sorry. We add actually magnetic field because we thought, oh, maybe with magnetic field we do split. Nothing happened on top, but we just had a normal, you know, behavior due to magnetic field, so the Zeeman splitting.
If I can make a small remark, I think because of symmetry in this system, DM interaction is not allowed. There are other rutile materials where the spin is not along Z, and there you can have a DM, but not in this particular.
Exactly,
order.
exactly. Not in this type of magnetic product. But in the dynamics, it must appear.
Okay.
Thank you.
Yeah, but
I
the
think
second
that's
order.
another question from the Zoom. I think it was Jaira.
Yeah. So anyway, that's a good conversation that's going with this. Oksana, thank you for the talk, by the way. It was really wonderful, and it's never at that low enough level. This is really very clear exactly what you did and all this stuff. And particularly, I also agree that the models themselves have to be as simple as possible, but not simpler, but not to add too many, because then you can add, you can create the elephant very easily from many, many terms. Yeah. And as you say, from some of the systems, you don't have, the Dzerzhinsky-Moria, by symmetries. Some of them are not contributing. But my question was a little more, from the point of view of the level of importance of a neutron scattering. I guess you're saying that neutron scattering itself is telling us the particular ordering that you have in the spins by fitting to a model, right?
Yes.
How strict then how safe can we say that this is a collinear versus non-collinear? Because it's a fundamental question to us for the altermagnets that you say, do we have collinearity? And then, of course, once you have the collinearity, it's quite easy from the symmetry to say yes or no. That's a yes or no question. And then later on to see which ones are the ones that are the magnetic contributors. They can do X-ray, of course, to actually do more element-specific type of questions. Yeah, for particularly those insulators where you can do
Very
crystal
good.
one.
Very
My
good.
question is just that how discriminatory it is.
Yeah. So there are several levels of neutron scattering, neutron diffraction. So this pattern, which I showed, it's powder. It's everything is averaged. And everything, all Qs are which are spherical, right? Even all this is averaged. You have just the lengths of Q, and from such measurement, and especially look at Q is quite small, so you can have a rough structure. So this dipole approach having antiferromagnetic moments, that's completely correct. Now, if you want to dig further, you probably should go to polarized neutrons.
Polarized neutrons,
First of all, you
exactly.
have to go to single crystal. This will be giving you much more than
How thick of a single crystal do you need? Let me put it this way: how thin can you go and still get a
So I'm
reliable
actually
result?
responsible for single crystal diffractometer. So whenever a user asks me this question, I tell, look, it depends. Tell me what you want. Because it depends what level of question you are putting. If it is a crystal structure, if it is a magnetic structure, I would say it's 0.5, 0.5, 0.5 millimeters crystal is good, because then I don't have problem with dynamic scattering, with systematic errors. Now, if you have a holmium crystal, which 10 magneton bore, or you have copper crystal with 1/2 magneton bore, that's also then will be scaling you the size. Also, if you want to see third harmonics or a small canting, probably better to go to larger crystal. The problem with crystals and single crystal diffractometry is you have domains, which usually people forget about. But there are some kind of domains which are then averaging also information.
How large is the spot of, so are you sensitive to entire crystal, or can you
Yes.
focus
The,
to
the,
just
the,
the
the
entire one?
good experiment is like relying on the hope that I mean, if we are collecting data set, right? If we want to have several reflections, we are to have, like with X-rays, the crystal illuminated by the beam.
I see.
But beam, I think, size is not actually a problem. Usually it is really that the signal should be strong enough. But now we discuss powder, single crystal, and there is another very, very great technique. This is polarized neutrons.
Yeah.
And for example, if you are asking about if there is a counting of the moment or not, I would be spending no time to measure that with probably powder and single crystal. I would immediately go to polarized neutrons, because polarized neutrons can distinguish nuclear, which is structural, and magnetic contributions. And this is giant. Like if you see, signal of, it increases.
Finite magnetization
It
will show up
increases a lot.
immediately. Yeah, exactly.
Right. For sure, you pay each
Yeah,
better.
it's quite costly. Yeah.
You pay by your size of the crystal should be larger, because when you do polarized experiment, you're cutting intensity.
Intensity.
You
Yeah,
cannot
exactly.
polarize neutrons. You're just picking up from the beam those which are polarized correctly. So 3 times here, 3 times there. So it is 10 times less flux, and so your sample is to be then large.
Great. Thank you so much. That was a really instructive talk.
Thank you.
Probably the last question. Please, Alexander.
Yeah, okay, maybe I have a few, but let's minimize to one. It was interesting thing about chiral magnons. Chiral magnons, you say, but I didn't see chirality on these maps. Where it is.
So we decided, before making this complicated experiment, seeing the splitting of the magnons and proving that they are chiral, let's first.
Not here, but you shown these maps with magnons. The modeled, right? Modeled maps of magnons distribution.
You mean this one?
Beginning, no,
The blue one is one chirality, the red one is another chirality. I understood your question correctly.
Okay. No,
if you are asking about the last experiment, which I mentioned, this is manganese telluride. You see here you have splitting. We decided we go with non-polarized neutrons just to see if there is splitting. And when we would see splitting, then we would hunt for polarization, because once more polarized experiment is much more complicated. And you cannot polarize neutrons at very high energies. Just
the question was about your first part of the talk when you showed the map of magnons. And but okay,
you don't have so many slides, might be good.
Later, I think so.
This one?
No, it is just very beginning of the talk when you shown this one.
Okay.
So and you said about chirality. You mean that it is just a different color here, or this map is chiral?
Yes, exactly. So this is a cut. So this is this whole spin dispersion. This is from Paul McClarty actually paper, and then you just cut it at different energies, and then you are getting one chirality, another chirality. So it splits. It is split, and it has different chirality.
Yeah, understood differently. Okay, thank you.
Okay.
Thank you very much. So let's thank the speaker again. So now we have to end our session.